may get started here. Our topic today is non-parametric statistics. This will be our last seminar for the year, or academic year, I guess. We'll start back up again in September. Oh, let's see. Can you, Lou, can you send your question on the either the chat or the question Q&A? Because I can't. If you have one. Okay, well, let me get started. Oops, here we go. Oh, okay. Let me see if I can mute and turn it back on. How about now? Is that better or not? Okay, well, let me get started then. Our outline for today is to first of all take a look at parametric statistics, and then we'll contrast that with non-parametric statistics. And first of all, just briefly mention some non-parametric statistics based on ranks, and then we'll look at resampling, non-parametric statistics, the bootstrap, jackknife, random permutations, and then I'll finish up with some comments about those. So when we talk about parametric statistics, what we mean is that we're using some theoretical distribution to model the statistic of interest, for example, the mean. And a theoretical distribution is defined by at least one of three parameters: the central tendency, the dispersion, or the shape. And so all of the theoretical distributions that we'll just look at here are defined by at least one of these, sometimes two. And so the most familiar one to everybody would be the normal distribution. And it's defined by two parameters, the mean and the standard deviation. And you can see that in the formula for the normal distribution that involves the mean and the standard deviation. And the normal distribution is infinite in the sense that it represents, if we're going to use a distribution to, say, calculate sample size, that it's an infinite distribution, or we assume that we would have an infinite number of subjects or patients for our study. So some characteristics of the normal distribution: the mean, of course, the mean, the median, and the mode are all equal, and they all occur where the slope of the curve is zero. In other words, right at the apex of the curve. And at the inflection point, where the curve changes from concave to convex, is one standard deviation either side of the mean. And essentially two standard deviations is about 95% of the area under the normal distribution. And so we can standardize the normal distribution by subtracting the mean from each value and dividing by the standard deviation. Actually, we can do that with any any variable that's has some interval measurement or continuous measurement. And so in this case, if we do this, then the standard normal distribution has a mean of 0 and a standard deviation of 1. And this is typically called the z-score. And so we can compare variables that are measured on different units by standardizing them. So other theoretical distributions that are really common that you'll see and you're probably familiar with, the chi-square, the t-distribution, the Poisson distribution, which we use for count data, and then the f-distribution that's used in analysis of variance. The thing about these theoretical distributions, though, is they're all sample size dependent. And as sample size increases, in other words, gets really large, goes to infinity, then these distributions tend to be a normal distribution. So here's an example of the t distribution with different degrees of freedom, where the actual t distribution has an infinite number of degrees of freedom, but the degrees of freedom here, 1, 5, and 25, and so you can see as the degrees of freedom, which is essentially dependent on sample size, gets large, it tends towards a normal distribution. And the thing about the t distribution is that for small sample size, the tails are of the distribution are thicker than the actual normal distribution, as you can see here. So here's the chi-square distribution, and you can see as the degrees of freedom get larger, it looks more normally distributed. The chi-square, or not the chi-square, the Poisson distribution is for small degrees of freedom skewed, but as you can see, as the sample size gets bigger, it tends to look more normally distributed. So to kind of review here what we mean by degrees of freedom that define the sampling distributions. Basically, what it means is it's the number of components of a statistic that are free to vary. And so just as a simple example here, if we have 3 numbers and their sum equals 100, then we can ask, okay, well, what number can x1 be? Well, obviously, it can be any real number. It can be even a negative number. And the same thing with x2, it can be any real number. But let's say that x1 equals 10 and x2 equals 20, then x3 has to be 70. So in this case, we would have 2 degrees of freedom. We have 2 components that are free to vary, but the other one isn't. And where this comes into play is, for example, in calculating the standard deviation, which is equal to the sum of the difference between each variable and the mean of all the values, that's divided by n minus 1. And why is it divided by n minus 1 instead of n? Well, it's because we've already estimated one statistic, and so the mean, and so we have a loss of 1 degree of freedom. So that's why when you compute the standard deviation, it's the denominator is n minus 1, not n. Okay, so there are a number of non-parametric rank tests which are in any statistical software, and you can use those if you think you need to, if the distribution of your outcome variable is not normally distributed, or just but it turns out that oftentimes they will give you essentially the same thing as the parametric test. So the Mann-Whitney U test, also known as the Wilcoxon rank sum test, that's would be an unpaired, and parametric test would be the unpaired t-test. The Kruskal-Wallis one-way ANOVA for ranks, that would be comparable to one-way analysis of variance. Then the Wilcoxon matched pair sign rank test, that is analogous to the paired t-test. And then we can do what's called a k-sample test for equality of medians. So this tests whether the medians are of two distributions are the same. The thing, though, is as the sample size increases to around 200, give or take, these tests end up using the normal distribution. And so for larger sample sizes, they essentially turn to the normal distribution to come up with a p-value or probability for the test statistic. And then there's a couple of rank order correlations where we use ranks instead of the typical correlation coefficients, Spearman's and Kendall's rank order correlations. What I want to focus on a little more than that, though, more so than the ranks, is the resampling statistics. And so here we have the three ones that we'll talk about are the bootstrap, the jackknife, and random permutations. So the bootstrap is basically randomly sampling our data with replacement. So in other words, you calculate a statistic like the mean, sample the number that are typically in the sample, the N of the sample. So if you have 30 patients or subjects in your sample, then you will take a random sample of 30 patients, but each time you draw one, you put it back in the pool to be randomly sampled. And so what that means is that some values, some data points can be resampled again or picked again in the bootstrap. And so typically what we do is we do a large number of bootstrap samples, which usually are anywhere from 250 on up. 250 is kind of the recommended minimum for calculating variance or a standard deviation. And basically what it does then, it creates a distribution of some statistic. And so we can use that for variance estimation, calculating the standard deviation, confidence limits, and we can use it for model validation as well. What we find though, is that when you bootstrap data, that there will be some values that will not be selected. And it turns out that this is about 30% of your sample. And so I have just an example here of just 10 values where we've sampled by bootstrapping with replacement. And so X1 represents the ones that have been bootstrapped, and you see that we have 3 values that are left over that weren't selected in our bootstrap sample. The terminology for this is those that have been bootstrapped we call bagged, and the ones that are not used are called out of bag. But you can see that each time we do this, like 3 different examples here, X1, X2, and X3 are bootstrap samples out of the 10 observed values, and we have about 30% that are not selected each time. Sometimes depending on what the issue is or the question is, out-of-bag values are used to compare with the bag values for, say, like two different groups. So, for example, we can use the bootstrap to estimate a 95% confidence interval. And so the example I'm going to use here is cost data, which is typically right skewed. Sometimes it's really right skewed. And so if it's skewed, then a normal base 95% confidence interval may not be entirely accurate. And so what we want to do to estimate a 95% confidence interval is bootstrap the data. And as I mentioned, for a confidence interval, you want to have at least 250 bootstrap replicates. And so then what we do, once we do that, we will mark the 2.5 and the 97.5 percentiles of the bootstrap distribution, and that will be our 95% confidence interval. And so I have an example here that I'm going to use from a cost effectiveness study that we did some years ago. And so in this data set, we have actually quite a large data set, some 9,300 different patients. And so we have their total cost, which would include hospital costs and so on. And then we have their quality adjusted life years. And so if we want to estimate the 95% confidence interval for the total cost, we might want to bootstrap it rather than just use it with the normal estimation. And this is a typical example of cost, hospital cost data or cost effectiveness data where it's highly right skewed. In other words, you have most of the values on the left side of the distribution, and the more extreme values tail out to the right. And so if we were to, and obviously the mean and the median would be quite different or maybe quite different. And so the 95% confidence interval might be different as well. So I have an example here where we have calculated the 95% confidence interval, and I've done that for a different number of replications of the bootstrap, 250, 1,000, and up to 10,000. So of course, every time you do a random selection with replacement, you're going to get a slightly different or even maybe sometimes fairly large difference in estimation of the 95% confidence interval. But in any case, these are all legitimate estimates of the 95% confidence interval. And so you can kind of decide how many replicates you want to do. But they're, it's really easy to do in bootstrapping, and I believe most statistical software have bootstrapping as a program in their list of programs that you can just click on and do. So when we do cost-effective analysis, though, what we do is we call the dual bootstrap. And so in this case, I have the same cost data here, the qualities, but also we have two treatment groups indicated by one of as the treatment group and 0 as the control group. And so when we do cost-effective analysis, we have to take both the total cost and the quality adjusted life year for each patient. We can't just get a random or a bootstrap sample of total cost and then do a different bootstrap of the quality adjusted life years. So we have to take them together. And so that's why we call that a dual bootstrap. And when we do that, then what we want to calculate is the difference in cost divided by the difference in effectiveness, which in this case is our qualities, or the difference between, say, the two groups. And this is the incremental cost effectiveness ratio, or the ICER, which is just the difference in mean cost divided by the difference in mean effectiveness, however mean effectiveness is defined. And so when we calculate this, we've taken, we bootstrap both the cost and the effectiveness at the same time. And then we get, when we plot it, then we get a graph that looks like this, where each dot indicates the mean effectiveness, and on the vertical axis, the mean cost difference. And so that way we can tell whether a particular procedure or treatment or whatever is cost effective. So a complement to the bootstrap is called the jackknife, which is a leave out one statistic. And so basically what we do here is we have a data set. And so what we do is we take one value out of it, and we calculate our statistic based on that. So if we have 30 observations, then we'll calculate the statistic based on 29 of them, taking one out. Then the one that we took out, we'll put back in and take the next one out, and then recalculate our statistic. And we do that until each value has been left out. And this is, again, used for estimating variance and confidence intervals. So I want to give an example here where we did this in a study from a few years ago, where dermatologists and PCPs, primary care physicians, were to rate lesions in terms of whether they would likely do a biopsy or whether they thought they were melanoma or not. And so this is the data basically was 30 photos of pigmented lesions, and then 2 questions: the likelihood that you would biopsy this lesion, which was rated on a scale from 1 to 10, 1 being highly unlikely and 10 being highly likely, and then B, which is just a yes or no suspicion that this is a melanoma. So these are some of the different pictures that they had to look at, and then make a rating of what they thought they were, melanoma or not, or how likely they would be to biopsy. So here's an example of one PCP's data. And so we have 30 pictures here. This is for question A. So this is rating the likelihood of biopsying. And so you can see there that for the picture number 1, this physician rated it 10, highly likely to be a biopsy, and thought it was a melanoma. And, and so we did this for 30 different pictures. So what we want to do, though, is compare the dermatologist with the primary care physicians. And so we'll do this using receiver operating characteristic curves. We have 103 dermatologists and 127 PCPs. So how do we do this? Well, obviously there's variability for each rater, dermatologist or PCP, because they have 30 different pictures to rate. So here is plots of the area under the receiver operating characteristic curve for the dermatologists and the primary care physicians. The first one for question A, and then the second one for question B. So you have 100 and some ROC curves for both groups. And of course, you can't really tell by much from these plots, except that obviously the there's a lot more variability among primary care physicians than there is among dermatologists. So what are we going to do? Well, we're going to compute an area under the curve for each rater. And then when we do that, we want to compare the average area under the curve for dermatologists and PCP. And so what we want to come up with each rater with one AUC value, and then we can just do a t-test for differences in the mean area under the curve. But remember that each area under the curve for each rater is based on 30 patients or 30 pictures. So we have sampling error associated with each AUC within each participant. And so how we're going to do that is we're going to jackknife an AUC for each rater, leaving out one patient. And so the data then for each rater will consist of 30 pseudo AUCs, each leaving out one patient. And by doing that, we then obtain the variance, and so we can compute then a single AUC rather than 30 AUCs for each rater. And so we'll get like a mean and a variance for the 30 AUCs for each rater. So here's an example of the same, whoops, let me go back here, for the same physician that we looked at last time for question A. And so here we have our 30 pictures, and then this is the AUC, the area under the curve, leaving out the picture. So 1.15 is the AUC, which is, more than one, but that sometimes turns out that way, leaving out picture number 1. So then we put picture number 2 back in, take out picture number 2, and recompute the AUC. And so we do that down for all 30 pictures, and then we can come up with one AUC for this particular physician. And then, so for question B, we can then use just sort of standard software for the having the different standard deviations per stratum for the for each physician type. And so when we do this, just using a linear model here, we get the estimates for the PCP using the dermatologist as the reference value here. And what we get then is our regression equation where the intercept is 0.845, et cetera. And then the regression or the regression coefficient for physicians is minus 0.048. So now we can then calculate an average AUC for each physician type using these values. And so we can then use standard software here. I think I did this in S, but it would probably be the same in R, where we're going to look at AUC as a function of physician type. And so when we solve our equations, this is the first one here, the 0.845. That, remember, that was the intercept. And then the minus 0.048, that was our regression for physician type. And so if we have PCPs, then it'll be this plus 1. then minus this. So we get a AUC of 0.8 for the PCPs, and for the dermatologists, it's the same thing, except now this is a -1. And so for the dermatologists, it's nearly 0.9. And so we can see that there's a fairly big difference between the two. And so this is actually what we call a semi-parametric model, where we've used a non-parametric jackknife to estimate variance and means. And then we use a mixed effects model, which is a parametric test. And this accounts for multiple raters with, we have correlated data here, obviously. And those would be random effects. So we can do a fairly complicated analysis here to get at comparing, in this example, physician types and AUCs, area under the receiver operating characteristic curve. So that would be fairly complex use of the jackknife. Here's a more simpler one. The jackknife is almost invariably used anymore in meta-analyses. And there are a couple of things, obviously, as we mentioned before, we can estimate effect size and variance. But using the jackknife, we can also identify influential studies in our meta-analysis. So an example here where this was done in this article that appeared in the European Heart Journal a few years ago. So our primary outcome was a composite pooled incidence of all-cause death and non-fatal MI. So if your patient had one or the other, the outcome would be a positive, be a yes. If they had neither, then that would be no or a 0, as it's usually coded. So I won't go through all their methods here, but the one I want to point out here is that they did a jackknife sensitivity analysis for each of their outcomes. They had several different outcomes to evaluate the results and the impact of each single study on the summary estimate of effect. And so what they're doing is all the studies they have, they're taking out one, recomputing the effect size or whatever the outcome of interest was, and putting that one back in, and then taking out the next one and computing it, the statistic of interest again. And so here is, this is sort of hard to see, is their forest plot where they have all their studies. And I believe this is stated in person years. So you can see that the estimated effect here is of overall is 0.32. And so what they would do then is they would redo this and each time leave out one study and then recompute the either the effect size, or I believe this is the rate per person years. And then this is the same thing. We're now we're looking at an effect size here. So again, they're doing the same thing, leaving out one study. And so they don't actually give you the value of the resampling or of the leave out one, but they said it's hardly any different than the one that was calculated with all the variables in there. So the last one that I want to talk about, the resampling statistics, is random permutation. And so now we're going to do random sampling of our data without replacement. Remember that our bootstrap, we did random sampling of the data with replacement. And so what this could be used for, or is used for, would be used for, is basically non-parametric hypothesis testing. And so what we do is we draw a random selection of patients from our data, regardless of what treatment or therapy group they're in. And then the remaining patients that were not selected are assumed to be the control or the placebo group. And so the difference in statistics, so for example, if we're calculating a mean, we would do that for each random draw, and calculate, say, the difference in means or the difference in proportions, whatever we're doing. And we do this then a large number of times, and it yields a proportion of differences that are greater than or equal to the observed difference, or if we want to just test whether one is greater than the other. In other words, what we're going to get out of this is the p-value. And we do a really large number here, usually on the order of 40,000. And this, some years ago in the Journal of the American Statistical Association, there was an article where the author sort of looked at this, how many do you need to do? And he came up with a number that was, and I don't remember how he did this, but it was like 38,000 and some, to be fairly confident that your, p-value was at least correct. So in programming this, I just, use 40,000 with, since it doesn't really matter in terms of time it takes to do the random draws. So I want to go back to our cost data, and this time what we'll do is we'll compare the treatment groups with respect to their qualities, their quality adjusted life years. And so we want to, first of all, we'll look at the distribution of the qualities. And you can see that again, it's obviously not normally distributed. Now we have data that's highly left skewed. In other words, the most of the values are to the right, and the extreme values or different values are skewed to the left. And so we would look at this and say, well, maybe doing a parametric test wouldn't be the best thing. So what are we going to do to test whether there's a difference in qualities between the treatment and the control group? So let's do just a regular parametric t-test and see what we get. And so again, we have a fairly equal number in the groups, 4652 versus 4656. So a little bit difference, but not much. And so when we do the t-test, we get this difference of 0.05 in terms of the mean qualities between the two. And so is this statistically different? Well, if we're testing the hypothesis that there is a difference, then we get a p-value of 0.02, which would indicate there's a difference between the two groups. And then if we just want to do, this would be like a one-sided test, just test the difference, whether the one group has a greater mean than the other group, regardless of how big it is. That's also statistically significant. So, and we might want to do this because our data is not normally distributed or even close to it. We'll do a random permutation test where we will randomly draw 4652 observations, regardless of treatment group, without replacement. And so when we do that, then the remaining 4656 will be our control group. And so then what we do is we want to test whether the treatment mean quality is greater than the control mean quality. which is just, it's either is or isn't. And so we're going to do this our 40,000 times. And so this is actually fairly easy to do. So our question is going to be, out of 40,000 replicates, what proportion of treatment mean qualities is greater than the control mean quality? And so here's a little R program that does that. So first of all, I am going to identify the CON as a control group. It has 4656 patients in it. And then my QDIF vector is going to be 40,000 long, because that's where I want to keep track of how many times the treatment mean was greater than the control mean. And so I just do a loop here for I in 1 to 40,000. The TRT, the treatment group, I'm going to sample the IDs 4652 and replace equals false in this case, because remember I'm not I am replacing each after each draw. And so then that's my treatment sample. And so then my control sample is just going to be the ID or ND here, as I have, of the not treatment group. And then my difference is just going to be the mean quality of the treatment groups minus the mean quality of the control group. And so when I do this, here's what I get. So it turns out that that 19,800 and some out of the 40,000 are greater than 0. And so to get my p-value, I just divided 19,000 and some by 40,000, and I get essentially 0.50. And so that's my p-value. And you might say, well, does that happen? Is that going to happen again? So you might want to, check it and see. So I do it a second time, and I come up with 20,000 and some that are greater out of the 40,000. And so my p-value here is about 0.5. So in this case, I'm going to have to conclude that the treatment mean is not different, significantly different from the control mean, or is not greater than, not. So that's how I get my p-value when we do the random permutation test. And so we can do this also by looking at one of the non-parametric rank order tests. And so since we're just comparing means or have two samples and want to compare means, we can do the Mann-Whitney test. And so these are the observations in the ranks. And so when they compute the test here, whether the control group is greater or the treatment group is greater than the control group, we get a z-score. And so again, it's using the normal distribution here. And so we get a probability of 0.03. So we would say it was statistically different. However, if we ask the question a different way, is the treatment group greater than the control group, then it turns out that our p-value is not statistically significant. It's 0.512, which is interestingly very close to the random permutation p-value. And so if we test, or if we compare our p-values here for our different tests, for our parametric t-test, we get a p-value of about 0.02 for whether the treatment is equal to the control, and also a significant if the treatment is greater than control. For the random permutation test, if we want to do whether it's equal, we actually come up with 0, or at least the time I did it, we got 0. So that would be really significant. And then if we want to test whether the treatment is just greater than control, we get a p-value of 0.497. And in the Wilcoxon, we get a significant value for the treatment equal to control? So we'd have to conclude that it's not. But if we're testing whether the treatment is just greater than control, then we get the p-value of 0.51. So you can see that if your data is not distributed more or less normally, then you can get different answers whether you use non-parametric test or regular t-test. And you might say, well, why are both of the t-tests statistically significant? Well, you remember that we have over 9,000 observations. So every parametric test is the p-value is dependent on your sample size. And so with a very large number like 9,000, most any difference is going to be statistically significant, even if it's really small. Okay, so I want to end up just with some comments here that parametric statistics are actually quite robust. And by robust, we mean that even if you violate the assumptions of being normally distributed or being distributed as one of the other distributions, that it still will give you a pretty good estimate of the difference and whether that's statistically significant. And often if you do the parametric and rank statistics, they'll give you the same result in the same conclusion, however, not always. Where the non-parametric comes in, where you actually need to do that, is to, when you have a statistic like the ICER, the incremental cost effectiveness ratio, which is a ratio of differences, there's not really a parametric test we can use to do this because we have two different variables and we have the ratio of the difference in the two. So we're not sure how that would be distributed. So we use the bootstrap to calculate a distribution, and then we can look at the characteristics of that distribution. So the bottom line here is always check the distribution of your outcome data. I'm not sure that's always done in studies, but oftentimes you'll see, well, the distribution may have been checked, and so it looks like it's not normally distributed, so we will do the non-parametric test. And so the non-parametric rank statistics, as I mentioned, will give you oftentimes the same conclusions, but because the data is not normally distributed, you may want to go with the non-parametric statistic. And then as I mentioned, if you have a statistic that is not really amenable to a particular distribution, any distribution, as when the random permutations would come in handy to do the statistical analysis. So I have a few minutes left if anyone has any questions, or if not, as I mentioned, this was our last seminar of the academic year. We'll start up again in September. So I'll stay on for a few minutes here if anyone has any questions that you want to ask using, I believe, the Q&A for that.